today is the second talk in a row by Eloy, which is fantastic. Thanks for agreeing to do that. Deep reinforcement learning and its neuroscientific implications.
Yeah, this is a paper by DeepMind with his main author, Matthew Bodnick. I think he's the head of the neuroscience department at DeepMind. And obviously DeepMind is very famous for their reinforcement learning, such as with AlphaGo. And I thought this is an interesting paper just from like a philosophical perspective. So they kind of introduced this idea of using reinforcement learning for neuroscience, or like at least using reinforcement learning as a computational framework to also understand neuroscience.
Is this related to reward is all you need paper of theirs?
No, I would say this is more directly like saying how deep reinforcement learning can help us answer some hypotheses we have about neuroscience, about representation of the brain. So they kind of, their main point is like, we've been studying neural representations with both from a neuroscience perspective and from a deep learning perspective. And we've done that in multiple systems, for example, vision, I mean, clearly computer vision versus neuroscientific vision. I mean, audition, which is just auditory, motor control, navigation, and cognitive control. We've tried to do this with deep learning, and we've tried to understand it from a neuroscience perspective. That's kind of what they mean. But the neuroscience application of deep learning can be traced back to the 1980s. And a lot of this stuff that we've been doing so far has been kind of the same things that we tried to do in the 1980s, but didn't have good neural networks for, like good deep learning algorithms for. So it's kind of a rebirth of those things, but the ideas are, I mean, they don't say this specifically, but the ideas are a little bit more, they go a little further back. So how they kind of like go about this paper is they first talk about the conceptual and historical introduction of deep learning. That's the first thing they talk about. Then they highlight some studies that have explored relationships between reinforcement learning and the brain, and then they talk about a broad set of topics that could be helped with using deep reinforcement learning as kind of a computational model, and then some caveats they have with deep reinforcement learning. So to introduce, so they kind of talk about like how unsupervised learning and supervised learning are like very common ways of like saying, hey, of studying representations. And they say in contrast to supervised learning, you don't get like explicit feedback for each action, whether it's good, but you get kind of feedback at the end more. Like there's more of a temporal component to it. And they talk about how, so they explain kind of, because this is a paper published in Neuron, so they're trying to explain this to people in neuroscience, how reinforcement learning works. And they say like, well, earlier work used to use tabular representations for states, but that's inefficient if you have a very large state space, obviously. And then the question arises of generalizing across states. And that's when you need function approximation. And that's where deep learning kind of came in.
A couple of interjections. From Hassabis's interview that I started listening today, he mentions a paper in the 90s that showed that dopamine system is a reinforcement learning system. So I don't know, like
They have that as well.
Oh, you have it. But also from the talk by Verbus that I was at the IJCN, he mentions interaction with Bartol and on the reinforcement learning like when they always were starting to do the work, and like he pointed to a paper that was before their work that suggested the idea. I wonder if other people cite Verbus for that. Interesting. I need to get his slides.
I need to check if they cite that.
Yeah, if they cite Paul Verbus, let me check while you talk. Sorry.
Yeah, no worries. But that's where the deep learning comes in, to generalize across states, to determine which action you need to take. I assume people are familiar with reinforcement learning as being like which next action do you take based on the current state and the previous states of your world you're in. But this is what it looks like. So with reinforcement learning, you have an agent you have actions that you can do, and you have an environment that you live in, and the environment you observe through observations and through rewards. So your environment gives you rewards back, but it also gives you observations at each time step. Then what you do is you kind of calculate the expected future reward given the current state and the actions you can do, and then you determine to take an action based on that. Whereas with classical deep learning, so they talk about unsupervised and supervised deep learning, it's more about like you have a guess, then you get the true level back, and it's this constant like telling you which one is good. Because one thing that's important here is that rewards are not given at every time step, right? So you don't know for sure if you're doing the right thing. Like if I want to open the door, there's a multitude of ways of opening the door, and I only know whether the actions I perform are correct once I actually open the door and I get the reward for opening the door. But I don't get like a reward every step, although obviously newer reinforcement learning try to maybe do that a little bit, but the main idea is that you get a reward once you actually perform the action. That is correct. Deep reinforcement learning, however, kind of mixes these both. So now you don't have an agent in like a very static way, but you have a kind of a neural network here that predicts things. Okay, so what are the fundamental differences for reinforcement learning with what they call traditional deep learning? So unlike unsupervised learning or supervised learning, you require exploration to determine which actions are correct to take. And so there's a trade-off between exploration and exploitation. Exploitation in this case means trying things out. So you first need to explore your environment to understand where the door is before you can open it, for example. That would be a good example. And one other thing that is important is that the representations for reinforcement learning are not shaped just by this label, for example, with supervised learning, but they're shaped by these exploration and actions. And that's an important aspect of why reinforcement learning is interesting to study, also with respect to neural representation of the brain, because we are obviously not just supervised.
Can I also add to that, kind of connecting the two slides in the previous one as well, with this neural network. So what we're learning there is a policy, and exploitation is kind of connected to a policy. And I don't know how to make an example, but like say a policy is wake up in the morning, go to work, do whatever your office boss tells you, come back and go to bed, and you get your paycheck in the end of the month. Okay, nice policy. You keep doing it over and over again, but your friend who was also doing it suddenly tried, oh, why don't I start my own company? That's exploration, try something else, and somebody fails, but two approaches, at least there are many, but one is policy learning. You need to learn that policy, and then it's hard to imagine what the neural network is doing there. What DeepMind has realized that the Q learning value function, value of your next action, is well, can be learned as a black box, as relative learning. So it's TQN, the first paper on the Atari game. It's I'm jumping ahead. Sorry.
That's I think the next.
I thought it relates to the previous.
No, exactly. No,
What
it does
is
actually.
neural
But so the way they talk about it, because they're trying to explain this to neuroscience, to a community of neuroscientists. So what they kind of say is like earlier work of reinforcement learning had issues with collapsing, and that's like TD gamma, which means temporal difference gamma. And one of the major breakthroughs, what they talk about is deep Q networks, which could play classic Atari video games. And so what they said was, although DQN was widely noted for attaining better than human performance on many games, the real breakthrough was simply in getting deep reinforcement learning to work in a reliable, stable way. It incorporated several mechanisms that reduced non-stationarity, treating the reinforcement learning problem more like a series of supervised learning problems upon which the tools of deep learning could be more reliably applied. And then the example they give is experience replay, which means that past transitions are seen randomly during training to kind of to make sure to mimic the random sampling of training examples that occur in supervised learning. And just like Sergey also just said, what they're doing here is predicting the value of each action. And they find it to be a much more stable approach also generally.
Is it still the case? Because I mean,
I
it's
think they still use that as kind of a basis for a lot of things. Well, a lot of the stuff that is related to neuroscience actually is probably kind of based on this DQN model. At least the ones that the examples they give. Okay, so where's the connection? Deep learning has been used to study neural representations, as we know, for vision, auditory regions, and stuff like that. But there's a big disconnect because these ways of studying neural representations do not help us understand goal-directed behavior within a sensory motor loop, which is kind of at the base of what humans also do, right? We have more goal-directed behavior and this kind of sensory motor loop. So reinforcement learning has already provided some theory with respect to mechanism learning and decision making. And they're going to give some examples, especially of that. So this is more, I would say this is more of the earlier work with supervised deep learning, where this is like based on Yamin's and DiCarlo's study, where they kind of show that single unit responses in various portions of the macaque ventral stream are similar to activity in the model that they use. Note that this is not just a normal convolutional neural network, but this is their, I think, because I've seen this figure multiple times before, this is their recurrent convolutional neural network, where they use recurrence in the network too. So this is one example, but this is a supervised and unsupervised learning. But more as an example of how we've studied neural representation before in the visual stream. This example is how reinforcement learning has been connected with neural function before. So this is a reinforcement learning example. I don't think this is deep reinforcement learning, but just normal reinforcement learning. And this is a very important link that Sergey also kind of talked about already, which is that phasic dopamine release and the temporal difference reward prediction error. So what that means is temporal difference reward prediction error. It's kind of like if I expect to get a reward and I get more reward, that is going to trigger the dopamine. But if I expect a certain reward and I get exactly that reward, then I don't get any dopamine. If I expect a reward and I don't get any reward, then it's like kind of lower.
What about if I didn't expect reward, but I got reward?
Yeah, then it's also higher. So the difference between what you expect and what you obtain. And so what they say is like the left side shows typical spike rasters and histograms from the dopamine neurons. And on the right side, you can see like a temporal difference reinforcement learning model. And this was something that reinforcement learning started doing that led to a hypothesis in neuroscience for dopamine neurons, and turned out to be a good hypothesis. So you can see the similarity here. That these, see the spiking here is very high here, which is the same in the reinforcement learning model. Here it's also high at the same time, and then here it's low. So yeah. And then the third one is, this is deep reinforcement learning. So we've kind of gone through supervised reinforcement learning and now deep reinforcement learning. This is a pioneering study. So this is just the start, is kind of how they're describing it. But what they're doing is, this study explained the responses of neurons in orbital frontal area 13 across many different choice sets involving 2 flavors of juice, in particular quantities of reporting neurons whose activity tracked the invert value of the monkey's preferred choice, the value of each individual juice, or the identity of the juice actually chosen. And so they find the same thing in deep reinforcement learning. So I looked at this figure, but it's a little bit hard to. So you can offer juice B or juice A. And these are like the ratios 1 to 3 or for example, 10-1. I think this is their neural network, essentially.
You mean the model?
The bottom, yeah. The bottom is the deep reinforcement learning model, and this is what you have on like a similar type of task, and this is like the monkey brain activities.
So character, the dependence character or functional shape of the dependence is similar. That's what they're trying to say.
Yeah. I think there's a better example too later on. That I'll talk about. Yeah, this was some of them are a little bit hard to. They don't give a lot of background information about these specific examples, but yeah, that's what this one is showing. Is like that the way the firing rate between quotes, I think, for the deep reinforcement learning network is similar to the spikes in the macaque, essentially. Insane. Okay, so again, they talk about this a lot of different times in different ways, but this the point they're kind of trying to make is like deep reinforcement learning is unique because it's different from both deep learning and reinforcement learning on their own. Like it's bigger than the combination of their parts because you have a very interesting interplay between the neural representations that are being learned based on not just, you know, this supervised signal, but, you know, actions and rewards and stuff like that.
But that's reinforcement learning. That's
Exactly. No, that's what I mean. That's what they mean. Like it's not just deep learning or not just reinforcement learning, but it's the combination of the two is more than the sum of their parts. That's what they're saying.
Don't understand why it would be still.
I can here. So deep reinforcement learning is more than this. When deep learning and reinforcement learning are integrated, each triggers new patterns of behavior in the other, leading to computational phenomena unseen in either deep learning or reinforcement learning on their own.
Okay, I need to digest. I don't.
So that is to say, deep reinforcement learning is much more than the sum of its parts, and the novel aspects of the integrated framework in turn translate into new explanatory principles, hypotheses, and available models for neuroscience. That's what they're saying. So I think what they mean is more like reinforcement learning on its own is very complex. Deep learning on its own is very complex, but the integration of the two leads to very interesting neural representations that are not found in either one of the two if you wouldn't combine them together. Because, for example, this is like an example of a reinforcement learning representation. This is an example of like a supervised learning neural representation. And this is like an example of when you combine the two together, you get something that is even more valuable, essentially. Like it's even closer to like the neuroscientific data.
But if you think about deep learning, we're still training it by gradient descent.
Mm-hmm.
It's just where we take that signal from.
I mean, when they say deep learning, they essentially just mean supervised and unsupervised learning. Deep learning. So they're saying like unsupervised deep learning on its own couldn't discover these types of neural representations, and reinforcement learning on its own couldn't either. But if you combine them, you get more. Which
oh, fancy that.
Yeah. This is so. I was not exactly sure why they showed this, but and it took me some time to uncover exactly what this was talking about. But okay, let's say you have two armed bandits, and
wait, two armed bandits or two armed bandits?
Two armed bandits.
So multiple bandits, each has two arms.
Okay. Two armed bandits.
Yeah, good question.
Yeah, you gotta clarify.
Such that the probabilities of reward payout PL and PR are drawn uniformly from between 0 and 1. And then what they're doing is, so they're saying like, okay, green is a higher trial number, and so is white. And they map the points based on whether the payout for left is higher than right, or the payout for right is higher than left. And what they're essentially saying is that when you train a lot of the different, if you train this model on a lot of different randomly sampled probabilities for which one is better, you get a deep reinforcement learning network that will develop the ability to adopt to new tasks of the same kind without weight changes.
What's an episode?
What?
An episode?
It's just a one two-armed bandit. So essentially they're saying like if you trained on 89,000 different two-armed bandits with different distributions. And these, by the way, are the PCA components for the hidden states of their LSTM, I think. Yeah. So they kind of like map them apart from each other. And that means that now it's very easy to generalize it. Essentially, that's what they're saying. Which is very interesting. It's kind of like meta reinforcement learning, is how they talk about it. So this is only by enforcing, so you don't do a different structure of the model. You just train a model using different reward probabilities, and that creates this good generalization, essentially. And then this is another one. There's a lot of examples. This is another example of the meta reinforcement learning. So how this works is it's also kind of like a two-armed bandit. But you have two targets and each of them can yield juice. And reversal means that you reverse which one gives you juice. And on the left is like spikes per second for a macaque monkey. And on the right is kind of this reward prediction error for reinforcement learning. And what you can essentially see is that they line up very well with each other. So you get the same effect of like the reward predicted error.
And this is literally two buttons for them to press or something like that.
Yeah. Yeah.
Why is it no noise in the model compared to the monkey brain? Like it's so.
Yeah, they're the RPE signals from an artificial agent. I think, I don't know.
Just binary, basically, on and off.
Yeah, it seems like it. Yeah, I agree. But I thought the same thing for this one, by the way. Like this one is also very, very like nice. I think it's
lots of filtering infras.
Right. No, but I think maybe it's because like the way the model does predictions is just a pretty like it's very like no noise essentially. That's the way it's doing predictions.
Yeah, that's interesting.
It would be interesting to see if you add noise to these predictions, if it makes it better. Okay, another example. So in this example, they're talking about temporal difference learning. So I've talked about this a little bit before. I talked about this before actually a lot of the time, which is like if you predict you're going to have a reward and it's more than you expect, that's good. But this is more of like a distribution. So it's not just one value. It's like, this is a very simplified example, obviously, because you have two choices. But generally, it's a distribution over multiple choices. So in the example of this mouse, you can get 0.1 microliter or 0.3, 1.2, 2.5, et cetera, et cetera. So it's more of a distribution over what you expect the reward to be. And when they incorporate that into these models, so that's like, this is what it would look like, for example. This distributional temporal difference learning is a much better representation of the neuroscientific of what you would expect in neuroscience as well. So what they say is essentially if you let the model predict a distribution over the return, that's much better, and it also lines up more with neuroscience research, but because this graph, the ground truth is the ground truth probability distribution over what this mouse gets back as reward, and decoded is decoded based on the dopaminergic activity of the mouse. So they can't decode this mode, it seems like, but in general, it follows pretty well the ground truth for the actual probabilities of what the mouse is receiving. And this blue line, they decode based on the dopaminergic activity of the mouse. So the dopaminergic activity of the mouse is predictive of the reward distribution. So that's interesting because that means that what they're saying essentially is like, that means that probably that's what mice are doing. They're not just predicting whether it's on or off, like whether they're getting a reward or not, or how much the reward is, but they predict a reward distribution. Okay. So those are a lot of examples. And then they talk about areas where deep learning may be interesting in the future. So like what would be interesting areas? So the first one they talk about is representation learning. And again, it's shaped by action and reward. That's why it's more interesting than, for example, supervised learning. And one of the reasons they give is that supervised learning, the representations are similar to the labels, whereas in deep reinforcement learning, the representations that are close together are representations that have similar functional implications. And they show that with this teasing plot, where here it's colored based on label, and here it's colored based on the value of that state. You can see that the representations are very different in terms of how they're structured in the latent space. So that's interesting. And they say, I don't think they put like this is better than that, but it's definitely different, a different way of looking at the representations. And they also show that the filters for convolutional neural networks are different if you use deep reinforcement learning, essentially, because it's now looking at different things, right? Okay. Then the next area is memory. And they give a few examples of this. So the first example of how memory, our hypothesis about how memory works can be shaped by reinforcement learning is that one of the first broadly successful deep reinforcement learning relied on experience replay, which is, so here they say, wherein past experiences are stored and intermittently used alongside new experiences to drive learning. This has an intriguing similarity to the replay events observed in hippocampus and elsewhere, and indeed was inspired by this phenomenon, and its suspected role in memory consolidation. So that's the first example they give of how memory and reinforcement learning are kind of tied together, or can be tied together. Then they talk about how the mechanisms in LSTMs have been proposed to be used in the brain. So they say, second, recurrent neural networks store information activations in a manner similar to what is referred to in neuroscience as working memory maintenance. The widely used LSTM and GRU architectures use learnable gating to forget or retain task-relevant information reminiscent of similar mechanisms that have been proposed to exist in the brain. So those are two examples of how memory and reinforcement learning kind of have an interplay. Then we have exploration. So one of the things they say is that it used to be often that people would use novelty to determine whether they should perform exploration in the reinforcement learning model, but now they're basing it more also on uncertainty. And they think that's interesting from the perspective of, is that also true for animals and humans? But there's also another one, which is hypothesis-driven exploration. And the properties essentially of hypothesis-driven experimentation make them an attractive potential tool for investigating the neural basis of strategic exploration animals, because now, because it's easier to investigate whether that happens in animals. Because it's hard to quantify uncertainty for animals, like what is an uncertain thing, whereas hypothesis-driven experimentation is easier to test with animals as well. They also name cognitive control and action hierarchies, where they say, like, for example, low-level systems operate autonomously and higher level systems only intervene at a cost. which is more similar to what's his name? Thinking Fast, Thinking Slow. That's the second one.
And,
Where deep reinforcement, the book,
yeah, Daniel Kahneman.
where deep reinforcement learning systems operate at different time scales at different levels, where they're slower at high levels and faster at low levels. So that's one connection where you can look at you can model deep reinforcement learning like that and then extract neural representations and look at whether they're similar to animals. And also social cognition by using multiple agents is a kind of a cheap and easier way of doing, is a computational way of analyzing social cognition. And then they talk about the challenges and caveats, which is that deep reinforcement learning still needs a large amount of data and has not been shown to be as flexible as humans in terms of like going to new tasks. And there's the issue with long-term credit assignments, like how do you update behavior based on rewards that happen far, far after you perform an action. So for example, if I determine to submit a paper right now and it gets accepted to a certain conference, that may have a very large long-term impact on my the impact could be very long-term, even though in the moment being tired and submitting the paper is you don't get reward for it. And the last one is that most deep reinforcement learning is still done in a very engineering context and not in a neuroscientific context to model the brain yet. So, but essentially they're saying, hey, why don't we do that though? Like it could be interesting because it's a pretty cheap and easy framework to start to train. Let's say we train like multiple agents in a social setting where they have to perform a certain task. And then we look at what happens. We can kind of get some hypotheses of how social cognition works in animals. And it's obviously much easier to do this on a computer if you can simulate it compared to doing it on actual animals. But then we have some hypotheses that we can test in actual animals. So that's it. If you guys have any questions, guys or girls.
I can ask. I have a question. It might not be a good question might be better asked outside of this. But one thing, I mean, like I've listened and read a few reinforcement learning papers and talks and stuff like this, but like I've never implemented it. And one thing that I'm kind of curious about is like I'd love to see like an implementation of like how you make the reward function backprop. Like it just for some reason in my mind. So it seems like the model takes in the same, like, I mean, it's such a general, I mean, reinforcement learning can be applied to everything. So, I mean, like, I think about it in terms of like robotics, but I mean, you can use it for like image processing and stuff like this. And it's hard for me to imagine like a good scenario to think through how to make it backprop. So like if you can kind of like go through the high level structure of an architecture, that would be cool. But like I said, it's probably not a good question for this format.
Well, I would say like you have an observation. It's like let's say input image and you have a reward, right?
Yeah.
Let's say the LSTM gets in 100 observations and it takes an action each time. And then after 100, it gets a reward. You backprop through those 100 states.
There are other ways.
No, but that's an example, for example. Like I'm just trying to think of.
There are ways that don't use backprop to update.
Yeah, but they're talking specifically about backprop.
Yeah,
Yeah. Like
I mean, that's one example. Like you would generally do there's multiple ways, right? So there's a lot of different reinforcement learning algorithms that now also incorporate unsupervised learning. For example, they don't only predict the next action, but also predict what the next state is going to look like. So like the pixels of the next state. That's one thing. they also do. So then the backprop is both through the prediction of the decoded input image, but also the reward at the same time. It can just also be only with respect to the reward. Yeah,
The reward function is always differentiable, right?
yeah. So yeah, if you get a higher reward, then the gradient is higher.
Okay.
Does anybody else have any questions?
Well, the main message here is that maybe we can learn something about the brain, right, from the way we do deep reinforcement learning.
Yeah, or use deep reinforcement learning as a computational, it's like a simulation framework. Like currently we're doing it in a very that's also what they say, like the second to the last point is like, most of it is currently done in like an engineering context. But what if we do these things? What if we train these networks specifically with the point of getting some hypotheses that we can then test in neuroscience, right? Like, what if we make it very similar to, for example, try to make it similar to the brain, because obviously we don't know everything about the brain, but make it similar to mechanisms in the brain, and then see whether the representations of both of them line up, right? Like things like grid cells and things like that. Like, are those neural representations? Where do they arise from? Do they arise from like reward prediction error? Do they arise from like it's? I think that's their point. I mean, grid cells don't arise from RPE, but they arise from needing a spatial location. But I think that's also the idea. Like, let's say you want to model social cognition. You could either do a study on mice, for example, and like watch mice and then write down exactly what the mice are doing. Or you could, for example, do, depending on the type of study you want to do, by the way, but you could also simulate agents with different goals, right? And see what happens. Is there some solution they converge towards? And
yeah, so some kind of exploratory research
Right.
or run a model. Because initially when deep learning wasn't, it wasn't yet cool, at least not in neuroscience. When we started submitting our proposals, the response was like, okay, well, you're trying to study one black box system, the brain, with another black box system. So what's the point, right? But here, what you're saying is the point is that we can have a black box system that we can stick the needles into, versus the black box system that it's harder to stick the needles into, and so we can just, like as you said, simulate, run one and see what we learn about.
well, yeah, kind of align, see whether the neural representations align, and what type of rules for the deep reinforcement learning agent are necessary to improve the alignment of the neural representations between the two systems, if that makes sense. Like when they started doing reward prediction, the neural representations inside of the model were much more similar to dopaminergic receptors and stuff like that. That's one way, and so we understood that probably that's something that the brain is doing as well, is predicting the reward and basing dopamine on that, right?
Well, from the paper, we sort of understood that already. We were just trying to align, in a sense.
Yeah.
It's not that the brain is doing that. We knew that the brain is doing that, but oh, look, the models are. Kind of thing.
Yeah, but I think this one is especially interesting in that sense. Is like if we now don't just predict the reward, but predict the distribution over the reward, that is even better of how the brain is doing it, right? So it's like you can test these hypotheses between the two, if that makes sense. Like you can kind of use, oh, hey, predicting the distribution is better in reinforcement learning. Maybe that's also a better explanation of what the brain is doing. Kind of that type of like interaction between the two fields, I think, is what they're trying to synergize in this paper a little bit. Is like, hey guys, we have this thing that is much like easier to simulate things with. why don't we try to exchange our ideas about how the brain is doing things and how we think reinforcement learning can become better. And there's probably like a vicious, virtuous cycle that neuroscience information can help, reinforcement learning can help, neuroscience hypotheses can help, et cetera, et cetera.
Yeah, that's the hope. Yeah, but my main thing that I'm hearing is its ability to simulate.
Yeah. I think, well, that's at least what I got from it is like, if we find ways to make it better, deep reinforcement learning, we should check whether that also maybe lines up more with how the brain is doing these things. Because that's interesting. And the other way around too, if we find new things about the brain, why don't we try to implement them into deep reinforcement learning and see if it makes it better?
Yeah, or if we can like discover deeper principles about how learning is happening.
Yeah, exactly.
Like I wonder if TJ, are you on about no, about upside down RL when you're trying to set, it's kind of like self-supervised, but like you're trying to set yourself tasks where you predict that okay, you will do it at a certain time or certain. Kids do that a lot, right? What is it? Challenging games or dare games and things like that. It's kind of more physical usually with abilities, but it's still learning. So, if upside down now. Okay. Yeah, that's very interesting. Any other questions? Anyone online? I guess in our group, in our center, reinforcement learning is still some kind of a useless, like as perceived as some kind of a side thing, mystery, and we haven't tried it. And, well, besides, we tried. TJ spoke about it multiple times, but
You must have a malleable student that you can make do RL.
Yeah, it'll be viewed that way until somebody does it, and then it won't be viewed that way. It's just because nobody's doing it.
Yeah.
Just take one of your students. And
Oh, I mean, like, I don't think that we framed the question appropriately for us, like for what we would use reinforcement learning for, right? Yeah, like if we framed the question well, then we'd all want to do it, I guess.
Yeah.
No, I agree with that. I mean, I've often thought about like how you could, like, you can use reinforcement learning as a framework for like predicting like next states, for example, because that's often what they do in model-based reinforcement learning as well. Right, is like trying to predict what happens in the future if you take this action. Like, how do you, like, I've been thinking about like, how do you apply that to like a time series, like the brain? You could think of actions as like, tasks, for example. Like it's a little wonky, like it's not really worked out, I think.
Yeah, or probably people have done that for the M series, right? You can think of actions just like moving the slider up or down, but the reward is if you can capture the trend of time series by doing this up and down. But LSTM is kind of already modeling that like more directly without
exactly.
the in-person training.
And that's actually one of the things they also say, right? Is like one of the breakthroughs of reinforcement learning was actually modeling it a little bit more similarly to supervised learning, where they get feedback at every stage instead of just at one stage, because that made it much more stable.
Yeah. But with the games, with AlphaZero, especially, well, in AlphaGo, I mean, it's only at the end of the stage.
Oh, no.
You get the feedback.
Yeah, but I think it does predict, right, the like reward and stuff. Like it does predict the value and stuff.
It predicts the value at each board position,
Right.
but the reward comes only at the end.
Right. Yeah. But I think it doesn't it also update based on like in the future, if it sees the same board, it does some experience replay, right? And then it updates that as well.
Well, only if it knows the outcome.
Right, that's what I mean. Yeah, that's what I mean.
Of course, yeah, that's the learning, reweighting is kind of. Yeah, thanks for going into it. Well, like a personal question in last 7 minutes. Why did you choose the topic?
Well, because I think it's just interesting to first of all, I think it's good to be careful in trying to say that there's like things have the same neural representation as the brain. And I do understand their argument. You know, the brain is not doing supervised learning, probably, like not just supervised learning. You know what I'm saying? Like it's, you know, so I think that's interesting. I think it's also, you know, I think also because we should just be looking more at the brain. Like we do so much DL and
Yeah,
so
yeah.
little brain, even though we're in neuroimaging. Like, you know what I'm saying? It's like, I think these types of opinion papers are not just for reinforcement learning, but I think they also span broader, namely, there should be more interaction and we should also be reading more neuroscience papers. And I think this is, I'm not going to just present like a full neuroscience paper because I don't think people would be interested in that, but I do think this is like interesting, right? It's like, hey, how do the two interact? Because they do, and I think we should also be moving towards that too, with our field.
Well, but maybe we should pick up a neuroscience paper, but not very specific, but just like explaining what is neuroscience. And that, like, it's also a broad field. In a sense, I'm thinking about it. A bunch of Huxley equations put together. That's all they do, right? And try to explain individual ones. But this is wrong, obviously. So, it's like, is it? There's also neuroautonomy, and like that's where we connect with brain imaging and kind of closer to home.
That's a really good idea.
Yeah, like just presenting a neuroscience paper,
Right, because
or inviting from someone from the Neuroscience Institute.
Right.
On,
Because
Yeah, I mean,
a
I
lot
think this is probably one of the clearest ways to generate hypotheses. I mean, that I've come across from deep learning. Like, I don't know tons about neuroscience, but I remember like a long time ago when we were talking about backprop in another group that like we always wondered if the brain had something like backprop, and I've seen that people have said that like the brain seems not to have backprop, but like it kind of like randomly prunes neurons and stuff. Like, I mean, like a big question I have is, I guess it's like, how does the brain update itself? But anyway, this is a pretty cool paper.
Well, I think it's, I think what I would say is probably that it's more similar to like Hopkins's ideas of like
The neurons decay.
well, no,
They're
like
just as they're-
Hopkins fields. Like I think they're still like one of the most neuroscientific. But it's like hard. There's papers that say they do, and there's papers that say they don't. Because like if you look at top-down neurons, that's maybe you could do gradients. Like
well, there are many mechanisms.
right,
I
it's
think that's
very
the problem.
yeah, it's a very hard. I mean, the credit assignment problem generally is just extremely hard, and I don't think there's one way the brain does it. And I think also a lot of people that argue that gradient descent can be done in the brain, they do tone down a little bit, like they simplify what neurons do a little bit. I don't think that's bad, but it's I think, you know, it probably isn't hard, just period, but it may be similar to like what we do with backpropagation. But you know, it's also a different like it's a different basis. Like the brain is an analog system, and we have like a non-analog system. We have a, you know, a computer, and so there's going to be differences, and I don't think that's bad. You know, we can take ideas and make them kind of similar, or like, you know, to what is actually happening. But I don't think it's bad if it's a little like I don't think it's bad if it's a little bit different. At least if we understand it on a sort of on like a philosophical context or something. Like it's always going to be hard to know exactly how a neuron updates, because even understanding a neuron itself is extremely hard. Like there's so many ODEs that are into play when you're talking about neurons. But if we understand the general idea of how they update, you know, that could be similar maybe to backprop. But I'm not, you know, I'm not opposed to that idea, but it's never going to be exactly the same. Just purely also because the hardware is different, right? It's like.
Well, there are many more mechanisms in the brain than
Right.
just the synaptic connections that we've modeled
Right,
initially,
exactly.
neural networks.
Right, so it's fine to think of it as like part of it is gradient descent or gradient updates like backprop. It's probably, you know, you probably won't be able to fit backpropagation on actual neuronal data because it's not going to work. But that doesn't mean that the idea isn't like, the general idea isn't important, like, it's like,
You mean
I
the
mean, more
general,
like understanding
general
things high
principle?
level is still interesting, even though it doesn't exactly follow the lower level dynamics of neurons, for example.
Well, but I find this question strange of why should backpropagation, one very specific way of doing gradient descent,
Oh, yeah.
be even similar to anything in the brain?
No,
It's
I-
more of a principle.
Yeah.
I
Yeah,
like,
that's also what I mean, yeah.
yeah, I like what Yannick Kuhn said there about like, there is no learning where you don't optimize some objective.
Right.
And the best way to optimize objective is gradient descent.
At
So,
least for us, for computers, right?
Well, even in principle, you want to find a minimum of a function. So how
No,
do you
no,
do
right.
that if you don't know anything about that function besides that it's say smooth maybe it doesn't have to be even smooth, but so you can't avoid gradient descent in learning. That's his point. It doesn't have to be done by backpropagation.
I'm kind of using the terms interchangeably. I mean, like I have like the same question about gradient descent. It's basically like, how is it doing gradient descent at all, or is it doing something that kind of mimics gradient descent but isn't? I don't know.
Neurons don't very often fire backwards.
No, not in that sense. They're doing update. They are optimizing some function. They are
Absolutely.
updating.
Yeah.
But how
gradient-
they're doing it doesn't have to. But why it even has to be like it's so different. There is a different way to do gradient descent. It doesn't have to be.
The one thing that I remember hearing, and it might not be true, but was with babies, like apparently they have more neurons or something, and as they learn, they prune away the ones that aren't used or something. I thought that was kind of interesting. It was kind of
Yeah,
like,
that's especially during puberty.
Not neurons, but connections.
Yeah,
That's how I heard it. But yes, it's more or less
Yeah.
what you're saying, William.
It's during puberty, especially.
it's kind of like you have like this like random circuit that you prune away to be like a refined circuit. That's kind of cool.
Yeah, okay, well, let's stop here. Thanks, everyone, and see you next week. Again, the schedule is at transcender.org/reading club in the calendar, and whoever is talking, you have it on your calendar. Well, Alex actually disconnected, but I think it's his day next day. Him and Mahfouz, who is not here, but because Alex was remote on ICML, watching it remotely, and Mahfouz was physical at ICML, and I went to IJCNN. So I think it will be our common kind of highlights from those two conferences of what was interesting at ICML and what I saw at IJCNN. So let's join next week for that.